So we live in a universe.
Yes.
How big is it?
That's a great question. It depends on what you mean by universe. So already it's complicated.
Oh, no. Oh, no. A few years ago, I came across a book by the astrophysicist Katie Mack called The End of Everything, Astrophysically Speaking. The book tells the story of our universe, how we understand its beginning, its expansion, and what we know about its future, including, well, the end of everything. We are only here for a little while, of course, and the universe will be here for much longer. But everything we've seen so far in our universe will inevitably die, and it seems the universe itself will as well. In short, there will be no season 2. I was so moved by this book that I wrote Dr. Mack an email to thank her for writing it. She replied, and we struck up a friendship. We make a bit of an odd couple. I'm a novelist by trade who barely passed high school physics, largely by being the kind of student my teacher did not want to have in class for a second consecutive year. Dr. Mack, meanwhile, holds the Hawking Chair in Cosmology and Science Communication at the renowned Perimeter Institute. But she is a patient teacher, and I am curious about the vast and strange universe in which I find myself. So we decided to make a podcast together about the history of the entire universe, including the parts of its history that haven't yet been written, and more broadly, about why we seek to understand what's keeping the stars apart, as E. E. Cummings once wrote. Here in the first episode, Dr. Mack helped me understand the Big Bang, which initially caused me a lot of anxiety, but then, by the end of our conversation, I learned something so phenomenally beautiful about the universe that I've been clinging with hope to it ever since, which is that we are not just made of stardust, we are also made of Big Bang stuff, with pieces of us directly born in the vast, first cacophony. Here's our conversation. Okay, I already have a lot of questions.
Okay, great.
I would like to ask you why there is a universe.
Oh. Why there is a universe?
And then I want to follow that up by saying that in my line of work, there's a famously boring question. That is the question that everyone asks, which is, where do you get your ideas? And in my wife's line of work, she's a curator of contemporary art, there is a famously boring question, which is, what is art?
Right.
Is the question of why there is a universe the astrophysicist version of those questions?
I think that it's just a question that really has no answer. And there are very few people in astrophysics or physics or cosmology, any of those areas, who are thinking really about that question, in the sense that there are some people working on, like, how did the universe begin? What started it? We kind of step away from that kind of question because that suggests purpose or intent or meaning in some way that there's no empirical approach to that.
To establishing purpose.
Yeah, yeah.
Do we know why there's stuff in the universe?
We don't.
Or
we really.
Am I
again
asking a why question, and you don't want me to ask a why question?
No, it's not. That's not a why question. That's an embarrassing question because our current understanding of the theories kind of suggests there shouldn't be stuff.
There shouldn't be stuff.
Yeah.
That's discouraging.
Yeah. There's this concept of matter-antimatter asymmetry. So antimatter is, it's kind of like a mirror image of matter in some sense. So there's an electron. An electron is a particle that's part of the atom. There's an antimatter version of electron called a positron, has the opposite charge, and there's some technical mathematical sense in which they're kind of reversed in some way. And if you take an electron and a positron and you put them together, they will annihilate with each other and create gamma rays. This is why, spaceships in science fiction often use antimatter as propulsion, because if you collide matter and antimatter, you get a big boom, right? Like if you started the universe with just a bunch of radiation and that radiation then turned into matter, it should turn into like an equal amount of matter and antimatter. So if you just had sort of radiation turned into matter and all that, and in the way that our equations kind of suggest it should work, you should get the same amount of both, and then they would just annihilate against each other. Like they would just, and then you would just have radiation again. You wouldn't have a whole bunch of matter and almost no antimatter, which is what we see. So if you got into the universe, everything we observe is matter unless there's been some kind of big high energy event like a pulsar or a supernova or some kind of high energy beam of gamma rays that splits into electrons and positrons. Then you can get antimatter in those high energy events, and you get a little tiny bit of it, and then it annihilates against the matter. But all the stuff in the universe is matter. Like all the stars and planets and all of that, that's made of matter. So there's way more matter than there is antimatter, which means at some point there had to have been something that like changed the balance, that created an asymmetry between matter and antimatter so that all of the antimatter would be annihilated away and there'd be matter left over.
Okay, so I know we're only a few minutes in here, but this point is really, really important, so I want to emphasize what Dr. Mack is saying here. Matter is everything you see in the universe. It's you, it's me, it's planets, it's stars and galaxies, and antimatter is essentially the opposite of matter. And when matter and antimatter meet, they basically cancel each other out, so nothing but energy remains. Based on everything we know about the universe, there should be equal parts matter and antimatter, but that's clearly not the case because you're listening to this and I'm here trying to explain antimatter to you. So there is more matter than antimatter in our universe, and that is the reason our universe exists, and we don't know why.
And we don't know why that happened. So we don't know the mechanism for that. There are theories, but we don't have an answer to that question.
But it had to have happened at the beginning, right? Because we know there's been stuff for a long time.
Yeah. I mean, our best guess is that it happened like sometime within the first like fraction of a nanosecond, basically.
What, really?
Yeah. Yeah, so it happened very early on, like before
Whoa. We know what happened in the first second?
Oh, yeah. Yeah, we can go down way earlier than that. We have a lot of information about the beginning.
We know what happened in the first second of the universe.
Yes.
The first nanosecond of the universe.
Yes.
The first fraction of a nanosecond of the universe.
We can go down with reasonable confidence to a microsecond. Well, actually, let's see. Maybe like a fraction of a nanosecond, something like that. We're pretty sure.
Okay.
We have good like theoretical and experimental evidence for what happened in that time. Before that, things get fuzzy. We have a really, really good theory, but we're not certain.
Okay. So that's great. That's great. We know what happened in the first fraction of a nanosecond.
Yeah.
What was that? Take me back.
Okay.
To the very beginning of the universe. And then after you tell me the story of what, the first second? The first nanosecond?
I'll get into the first minute or so, yeah.
How the heck do we know what happened in the first minute of the universe 13.8 billion years ago?
Okay. So I'll start with the Big Bang Theory. When people talk about the Big Bang Theory, usually what they mean is like they're like, oh yeah, I heard, the universe was a singularity, is a tiny infinitesimal point that exploded in all directions. And that's not really what we as astronomers mean when we say the Big Bang Theory. When astronomers say the Big Bang Theory, we actually mean something a lot closer to the theme song of the TV show The Big Bang Theory. Because I use this example because it's actually pretty good. In that theme song that says, the whole universe was in a hot, dense state, then nearly 14 billion years ago expansion started. And then the song goes on to other things, right? But that's it. So the Big Bang Theory is just the idea that the universe was hot and dense in the beginning. 13.8 billion years ago, it was hot and dense. And it's been expanding and cooling since then. The origin of that theory is the idea that currently the universe is expanding, right? So we observe that because we see all the distant galaxies are moving away from us. Essentially what's happening is that we see the light from all these very, very distant galaxies. That light is being kind of stretched out by the expansion of the universe. So what that does is it moves it from sort of visible light to infrared light as the wavelength is kind of stretched out. And it's a similar effect to like if a siren goes past your house and it goes into lower pitch, like that. The same kind of thing happens with light. When things are moving away from you, they get redder or to longer wavelengths. When they're moving toward you, they get bluer to shorter wavelengths. And this happens at all the different wavelengths of light, from radio to gamma rays and so on. So anyway, we see that distant galaxies are moving away from us. They're moving away from each other. There's more and more empty space happening all the time. The universe is expanding. It doesn't mean that like objects are expanding. It just means that there's like empty space in between objects that's expanding. And we've known that the expansion is happening. We've known that for a long time, since like the 1920s.
That's not that long.
Well, I mean, since we started to be able to know that like there are other galaxies, essentially, we started to see that the ones that are far enough away are moving away from us.
Right.
The conclusion you get from that is that if the universe is expanding now, it must have been smaller in the past. Like if all those galaxies are getting farther away now, they must have been closer together. And, if you push things closer together, it makes them hotter, it makes them denser. Like you can squeeze things and they get hot and dense. And so you can just kind of extrapolate and say, well, the beginning of the universe, things must have been hot and dense and really close together, right? And then you kind of keep going with that extrapolation. You arrive at the idea that the universe was this kind of hot, dense soup of energy in the very beginning. And that idea has been around for a long time. It's been kind of floated in different ways. And the kind of confirmation of that came in the 1960s when we started to actually see the light of that hot, dense soup.
So we know that the universe is expanding both because we can tell that galaxies are getting further away from us, but also because we can glimpse this hot, dense soup that the universe was at the very beginning. So we have two independent ways of knowing that the universe used to be a hot, dense place.
Yeah, essentially. I mean, one is kind of indirect evidence in the sense that, you just kind of extrapolate the expansion backward and you get that everything was close together. But seeing the light of the hot, dense early universe is very direct.
Yeah.
What's happening there is that, if you look at distant objects, you're looking at farther into the past because light takes time to travel. And so you look at the sun, it's 8 minutes ago. You look at nearby stars, it's years ago. Different galaxies, millions of years ago. You keep going with that. And one would expect that eventually you stop being able to see galaxies because you're looking at so far away that you're looking so far back in time that galaxies haven't formed yet. And if you look far enough away, you should be able to see that hot, dense, bright, shining universe. And it's counterintuitive because people think like, oh, if the universe was small, like there should be some direction that the Big Bang was, and you look toward that direction. But it's not. What it is that the whole universe was hot and dense. So imagine like a large universe, a large space, and the whole thing is filled with this like hot, dense plasma. And then the whole thing is expanding and cooling down. And if you're in one spot and you look far enough away, you can look far out into a part of the universe where, from your perspective, it's still in that early hot, dense state. It's very hard to picture.
I'm going to imagine incorrectly that we can either look to the left or the right.
Okay.
If we look to the left far enough, we will see that evidence of what the universe was like when it was hot and dense, because we can, if we see all the way out, and then we can also see that in any direction. Is that right?
Yeah, I mean, what we're seeing is we're actually seeing the universe as it was when it was hot and dense, because we're looking at it as it was 13.8 billion years ago. And if we look at a part of the universe that's so far away that the light took 13.8 billion years to get to us, then that means the light that's getting to us is the light from the Big Bang, the light from that hot, dense primordial soup. And so, yeah, we see this like wall of fire around us, this like shell of fire.
Yes. So is this wall of fire, which is a very helpful way of imagining it for me, is it equally far away in every direction we look?
Yeah, just because, like, the time that the light took to travel is the same in any direction.
We are in the center of our observable universe.
Exactly.
And so this wall of fire is the same distance from us in every direction. But if we were in a different galaxy, the wall of fire would also be the same distance in every direction, because that would be the center of the observable universe.
Yeah. It's very much like if you're standing on the Earth and you look out in all directions, the horizon is the same distance from you, assuming you're on a flat, like let's say you're in the middle of the ocean, so we're not getting complicated with mountains and stuff.
Yeah.
The horizon is the same distance in every direction. And it depends on where you are. If you're in a different part of the ocean, the horizon is the same distance in every direction, but it's not the same part of the ocean that you see. So there's your observable ocean, which is the part within the horizon. And we have an observable universe, which is the part within our horizon, which goes out to this distance that light could have traveled in 13.8 billion years.
Okay.
Yeah, and so it's kind of this weird thing where when we look out into the universe, we're like flipping back in time. We're like looking at this sort of scrapbook of the universe, because the farther away we look, the farther back we're looking. So we're kind of seeing the cosmic timeline very directly when we look out into space. And so we can't see, the Andromeda galaxy as it is today. We can see it as it was, millions of years ago. We can't see the sun as it is right now. We can see the sun as it was 8 minutes ago. However far away you're looking, you see it at a different time, because of the way that the light has been traveling. So when we look at something, billions of light years away, we're seeing it as it was billions of years ago. And that hot primordial soup, that wall of fire, is actually 46 billion light years away, because the light has been traveling for 13.8 billion years, but the universe has been expanding. So it's been carried away from us in that time.
Wow.
It was actually a lot closer when the light left it.
So as Katie just explained to me, everything is getting further away from everything else, and if you look far enough into space, you will see the beginning of time when everything was vastly closer together. It's so very wondrous and strange to be hurtling not just through space, but also through time in a universe that is not only expanding, but is expanding faster than it did yesterday. I'm astonished that's happening, but I'm even more astonished that we know it's happening. But maybe the weirdest part of this whole shebang for me is that it started and will also end. For each of us. How weird to be finite within a plausibly infinite universe. Anyway, that's why there's life insurance, a way to make things a little easier for those we'll all leave behind. Policy Genius is the country's leading online insurance marketplace, and with Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options offer same-day approval and avoid unnecessary medical exams, and Policy Genius has thousands of 5-star reviews on Google and Trustpilot, so check life insurance off your to-do list in no time with Policy Genius. Head to policygenius.com or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com. Policy Genius. You're a temporary part of a universe in which everything is getting further from everything else, which necessitates life insurance. That's not their tagline, and it is a little wordy. I'm workshopping it.
How big was it?
Okay, so we can talk about how big the observable universe was at various times in the early universe, but it's complicated because we think the universe is much larger than our observable universe, and it might be infinitely large.
You had me, but now I'm lost again.
I know. Yeah, so
how could it be infinitely large?
We have no evidence that there's any kind of edge to the universe. There's an edge to our observable universe in the sense that there's a distance we can't see, just like there's a horizon on the Earth. But there's no edge to the Earth in that sense. It kind of you can keep walking around the Earth and you just keep going forever. It might be that the universe is like that maybe it wraps around itself, maybe it doesn't. Maybe it's just infinitely large in all directions and you can just keep going in one direction forever. We don't know. We don't have any reason to hypothesize either it's infinite or finite because we don't have any evidence for it to have a boundary.
And it would be hard to find that evidence since we know that we can't see past the beginning.
Yeah, exactly. So we can't see past our observable universe, which is defined by, how far light's traveled since the beginning. And since in our observable universe, we see no evidence for an edge, if there is an edge beyond that, we wouldn't know.
And we never could know.
Yeah. So the whole universe could be infinite, and it could be just growing anyway, which is like a thing because you can have different sizes of infinities in mathematics.
So it's possible that the early universe was an infinitely large, hot, dense place, and the current universe is an infinitely large, less hot, less dense place. It's just that those are infinities of different sizes?
Yeah. Yeah, essentially. Yeah.
Okay. That makes me nervous. I feel anxious.
I'm sorry.
Personally, I would prefer – I liked the image I had when we started out, that it was just a singularity, that all the matter was just inside of an infinitely small point. That made me less anxious than an infinitely large, hot, dense space that led to an infinitely large, less hot, less dense space.
I mean, it probably isn't going to help, but you can also have a singularity that is spatially extended and still infinitely dense.
Yikes. No, that made it worse. No, you're right. That made it worse.
Okay, so we've been talking about the mysterious existence of matter and the expansion of our observable universe, but before getting too much further, I just want to zoom in on the idea of the singularity. The singularity is the idea that the universe was once an infinitely small point, and then it started to expand and has been expanding ever since. That's a story about the beginning of the universe you may have heard before, but it turns out it may be too neat of a story to actually be true. I'll let Katie explain.
Okay, but we don't know if there was a singularity at all, because when we do this timeline of the very early universe, it turns out that just saying there was a singularity and everything was super super hot and like infinitely hot and then it's expanded and cooled, just following that timeline doesn't work. Let me just kind of tell the story as we think it went, and then we can talk about why we think that.
Okay.
So maybe there was a singularity. We don't know if there was or not. The reason that people talk about a singularity, the reason that idea comes into play is that if you write down sort of the equations of how a universe can evolve, how space-time can evolve, then there's a solution to those equations. There's a mathematical picture that works where the universe evolves from a singularity, expands, and then either keeps expanding forever or evolves back into a singularity in a big crunch. So there are kind of different ways that can go. But those are consistent with the equations of general relativity, the gravitational theory of the universe. But if you actually work out like what the consequences of coming from a singularity and just expanding in a sort of in that normal way, if you work out those consequences, you get a universe that doesn't look like what our early universe looks like. So when we look at the background light of the early universe, the light that's at the sort of wall of fire in every direction, the properties of that light, essentially it's like it's too uniform. It looks to be basically the same in every direction in a way that wouldn't make sense if the universe really started from a single point and then expanded. And it's a complex story why that's a problem. It has to do with the idea that, there should have been kind of quantum fluctuations that changed the properties of the universe when it was very, very small, and then you'd see big changes in the pattern of the background light. So in the 1980s, there was a suggestion that maybe we didn't go just straight from singularity to expansion. Maybe there was a period of very, very rapid expansion in the beginning called cosmic inflation that kind of smoothed out the universe. Kind of like if you smooth out like a fabric or something or yeah, I guess that's one way to think about it. Like you kind of like stretch something out and make it really, really smooth. And then there was regular expansion from there, so that our expansion came from a universe that was already made very, very uniform by some really, really rapid expansion in the beginning.
Okay.
So we're kind of zooming in on one part.
So when we look at the wall of fire, the wall of fire looks far more uniform than we would expect if the universe began with a singularity because of certain rules around quantum fluctuation that should have...
Yeah, essentially.
Well, believe me, Katie, I am going to be oversimplifying.
That's fine.
We would expect it to be less uniform, this wall of fire, than it appears when we look at it. And that tells us that maybe what actually happened was that in the very, very beginning of the universe, there was an extraordinarily rapid expansion, much, much faster. Was it faster than the speed of light?
That's...
Oh, no.
I'm sorry. I'm sorry. I keep doing this. Expansion.
You're like, that's not an interesting question.
It's an interesting question. It's a hard question. Okay, because expansion, you can define the speed that 2 points are moving away from each other, but you can't define a speed of expansion because let's say you spread the fingers in your hands very quickly, right? When you do that over the course of like 1 second or something, the two fingers that were closest together at the beginning, they're still kind of close together. They've moved maybe like 2 centimeters in those 2 seconds. But the ones on either side of your hand have moved maybe like 10 centimeters in those 2 seconds. And so the speed of expansion of the speed that the two farthest ones have traveled is faster in terms of moving away from each other than the speed of the two closest ones.
So my thumb and my pinky have moved faster because they've moved further.
Yeah, they've moved to like 5 centimeters a second, whereas your first finger and your middle finger moved like 2 centimeters a second.
Right.
Right. So the farther away things start, the faster they've moved apart. If the expansion is uniform. So if your hands were like infinitely large and you did the same kind of like you just make them twice as big in 1 second, then there's going to be some distance where there's going to be
variations in the experienced speed of it or the actual speed of it.
The recession, the like separation speed.
Right.
So the separation speed of the close by fingers is going to be small. The separation speed of the really far away ones is going to be really fast. You can always find a distance in a uniformly expanding space where the expansion is faster than the speed of light, because there's always going to be 2 points that are being separated from each other at faster than the speed of light if the whole space is expanding.
Is this related in some way to what you mentioned earlier, that the universe is 13.8 billion years old, but the cosmic background radiation light that we see is like over 40 billion light years away from us?
That's related to the fact that the universe has been expanding the whole time that light has been traveling.
Okay.
And that those distant places has been moving away from us faster than any other part of the universe because they're the farthest part. So yeah, essentially. So the part of the universe that's moving away from us faster than light right now is like most of what we see in the universe, which is weird. Like we see lots of galaxies that are so far away from us that they are currently moving away from us faster than light. But it's because the light left them a long time ago and has been traveling toward us while they've been sort of rushing away that we still see that light. That light was able to catch up to us. But if they put out light now, it's moving away from us faster than light.
If they put out light now, we would never see it?
So it depends on that also gets complicated because the light can be moving, like the space can be moving, it can be pulling the light away from us, but then different parts of the space are sort of moving at different speeds. There are some things that are so far away now that even though they're moving faster than the speed of light from us now, as their light spreads out through the universe, it'll reach a part of the universe that is not leaving at faster than the speed of light, and then it'll start to move toward us again. And then eventually it'll reach us in the future. That gets really complicated. We need graphs for that.
Yeah, at that point, it's like a train leaves Boston going 80 miles an hour.
Yeah.
Another train leaves San Francisco. I'm out.
This gets into the stuff where like I tried to explain this to my general relativity students, and everybody looked at me with blank faces. Like this gets really complicated. But essentially, the point is that the speed at which things are moving away from us can very easily be faster than light just because space is expanding in between. Nothing's moving through space faster than light, but the space in between us and other things is spreading out so fast that our relative distances getting faster, getting larger very fast. So during cosmic inflation, everything was moving faster than the speed of light away from everything else, but like in a much more extreme way than is happening now, I guess. So there's a technical sense in which you can explain it through that, but it gets too complicated. Like you again need graphs, but the effect of it is like if you think of the universe starting as a singularity. Now this is something that always bothered me when I first learned about this whole question. It was that the problem with the cosmic microwave background being really uniform, the background light being really uniform, is that it suggests that like the universe was very uniform in the early times when the light was produced in a way that we wouldn't expect unless you have sort of a special setup. Now, people would say like, well, but if it was a singularity, then of course that it was all the same. It came from all the same thing. But the problem with that is that if you had that sort of infinitely dense, infinitely small thing that kind of is expanding, like because of quantum mechanics, it can't all stay perfectly uniform. Like there would be sort of fluctuations. And so you shouldn't be able to go from a singularity to, a perfectly smooth, perfectly balanced, everything is exactly the same temperature ball of fire. That just isn't how that would work. You should have some kind of fluctuations. And so what inflation does is it's like it zooms in on one tiny part of that ball of fire where the temperature is all the same. And it zooms into that and then uses that as the starting point of the whole universe now, the whole observable universe now. So that's the sense in which inflation like smooths things out. Is it kind of zooms in on a particular part of this complicated picture.
So rather than thinking of the beginning of the universe as an infinitely small point, we might think of it more like this. In the beginning, there were these different parts that were super close together and were sort of in communication and in balance with each other. And then, during a period of intense inflation, like the inflating of a balloon, all of these parts moved rapidly farther away from each other as the universe first started to expand. And this inflation works kind of like a cosmic microscope to help us see the quantum fluctuations that existed in the very early universe, but it also helps us to understand why, at least in terms of background light, super spread out parts of the universe are actually shockingly uniform. Like, whichever direction we look, it looks about the same.
And just to state the obvious, we don't know what came before this because we can't know what came before this because it invented the idea of before.
Well, yeah. I mean, so there are two senses in which it's hard to know things before. One is that if there was a singularity, then that singularity would have, you can't see through that. That would have been the starting point for space and time in some sense. The other sense in which we can't see beyond that is that if there was this cosmic inflation, then by its very virtue, it takes most of the information of that early time and just pushes it way outside of our cosmic horizon. And so we only would ever get to see a tiny piece of that early picture because of cosmic inflation, if that's what's happened. And so it makes it really hard to know if anything happened before that, like what it was. So cosmic inflation, takes the whole singularity problem and says that's not even an issue. We don't know if that happened or not. We can't have any information from before inflation in this picture. Like there might be ways to gather some information about like the setup of the universe before that, but it's observationally it's basically impossible because of that zooming in on this tiny piece.
Right. So the first thing we can know is that the universe was very hot and very dense, and then it began to expand through this process that we think was cosmic inflation.
Well, yeah, we don't even know for sure if cosmic inflation happened.
Okay.
But the hot, dense stuff that we see when we look out into the universe is after inflation ended. So it's after the inflation stretched out the whole universe, made it uniform.
Oh.
Then there was like a hot, dense soup.
Oh.
And then regular expansion.
Okay.
So the sequence is singularity, maybe, we don't know. Then cosmic inflation, and then hot, dense universe.
And so when you say we know what happened in the first second of the universe, as we're defining it, begins after this period of inflation.
Yes. Yeah.
And do we know how long this period of inflation lasted?
Well, so we think maybe about 10 to the minus 34 seconds.
Shut up.
So that's
what?
Real early. Yeah.
I was thinking like a few billion years. I was thinking like 2 to 3 billion years.
No, it was real fast.
10 to the negative 34 seconds is there's nothing that's that fast, right? Like I can't think of anything that would be that fast.
No, it was just a tiny, tiny fraction of a tiny, tiny fraction of a tiny, tiny fraction of a second. We think it was very, very quick, but the universe expanded by a factor of 100 trillion over that time, at least.
Oh my.
Yeah. So it was a very, very rapid expansion. So after that, we have a pretty good picture, and we can talk through the sequence of events after inflation ended.
Yeah.
So when inflation ended, there's still some controversy about whether inflation happened, where most astronomers think it did. When inflation ended, it created this big dump of energy into the universe that caused that hot, dense state to exist. So from there, we have a really good idea of what happened. And the reason for that is that we can calculate the temperature and density of the universe at that time. And we can study that in a few ways. And one of them is by smashing particles together in particle colliders to try to mimic those temperatures and densities and just see what it looks like. And so that's how we have this amazing story of the first second, because we can actually simulate that in laboratories by just creating those conditions. So for example, we know that there was something called the quark era, where the universe was this quark gluon plasma. So quarks are these tiny particles that make up protons and neutrons, and gluons are the force-carrying particles that kind of stick everything together inside an atomic nucleus. So there was this plasma of quarks and gluons that lasted until about a microsecond in the early universe. And during that time, there was a sort of reshuffling of the laws of physics that separated the electromagnetic force from the weak nuclear force, and all this kind of stuff was happening. But we have a really good picture of technically exactly what was happening during that time, where we know that there were quarks and gluons. We know that this electromagnetism and weak nuclear force separated.
And we're going to get into the fundamental forces in our next episode. But for now, we know that there was this quark soup, and that these fundamental forces were beginning to happen.
Yeah, so the sort of laws of physics are being kind of set up by this changing fluid of high-energy matter. And we know that because we can create a quark gluon plasma in a laboratory by smashing gold or lead particles together in the Large Hadron Collider can smash these particles together and create material that dense and that hot that we see that quark gluon plasma. We can actually sample it, basically, and we can see how the laws of physics are starting to change as you get to those really high energies. And then we know that at about 2 minutes, it all sort of cooled down enough for protons and neutrons and electrons to form. So before that, you couldn't have those particles because it was just too hot. Everything was kind of souping around. And then at some point, it cooled down just enough so that we have these nuclear particles forming. And then you start to get atoms, and that starts at around 2 minutes. And we can get into that a little bit more later.
So in the first second, there's this quark soup, and then those quarks cool off enough that we have protons and neutrons, and then that cools off enough that those protons and neutrons start to form atoms.
Yeah.
And so 2 minutes into the universe, we have some version of stuff that is analogous to the stuff that we see today.
Okay, So this part is really fun for me. So at this point, this sort of 2-minute mark, this is when you get Big Bang nucleosynthesis. So what Big Bang nucleosynthesis is it's the time when the whole universe was essentially like the center of a star. It was the same kind of temperatures and pressures as the center of the star. And in the centers of stars, what's happening is that hydrogen nuclei are coming together to form helium nuclei. You have this process called nucleosynthesis where you're creating these heavier atoms. You can make, in certain kinds of stars, you make carbon and oxygen, all that kind of stuff. So there was this time when the whole universe was as hot as the center of a star. And when that happened, you got these nuclear reactions happening. So hydrogen turned into a little bit of helium, and there was just a little bit of lithium and beryllium. Like there were a couple of trace elements of other things, but it's mostly hydrogen turning into helium. Like the whole universe was a nuclear furnace, just like the center of our sun, doing basically the same thing as what the center of our sun is doing, turning hydrogen into helium. And so at that point, you get, about a quarter of the nuclei or whatever become helium. And so the cool thing about this is so people talk about we're all star stuff because, stars turn atoms into carbon and oxygen and all these things that we're made of, right? We're made of carbon, oxygen, nitrogen, and so on. But most of the atoms in our body are hydrogen, just by number. Just if you count up the number of the atoms in our body, most of them are hydrogen. And that means that they were formed in that first 2 minutes of the universe. So most of the stuff that we're made of is actually Big Bang stuff. It's actually this primordial nucleosynthesis soup from the beginning of the universe.
So part of me was there?
Yeah. Yeah.
Literally part of me was there?
Yeah, the hydrogen in your body, those atoms first formed in that first 2 minutes of the universe.
So part of me, not in a figurative sense, was present 2 minutes in.
Yeah. Yeah.
Whoa.
Yeah. And as far as I know, most of your atoms haven't even been through a star. They coalesced from the stuff of the early universe, gas clouds and so on, and then sort of fell onto the earth, and then, you grew out of stuff that was on the earth. But yeah.
Wow. So earlier you made me feel very anxious.
Okay. I'm sorry.
By telling me that the universe was maybe used to be small and infinite and is now bigger and infinite. But now you made me feel very calm and connected to this universe by thinking that I'm not just made of star stuff. I might actually primarily be made of Big Bang stuff. So I may have been around, albeit not in a sentient form, for that whole time.
Yeah. Yeah, exactly.
Which makes me think that those parts of me will also be around for a while, right?
Yeah, I mean, the hydrogen nucleus is just a proton, and we don't have any evidence that protons decay. So your protons will be around for billions and billions and billions and billions and trillions of years. And there may be a decay time for a proton. The best limit we've got is it's got to be more than 10 to the 40 seconds or something like that. But it's a long, long time. So your hydrogen atoms are going to carry on.
I don't know that I need to be around that long,
Well, the scenery will change.
The scenery will change. The vibe will be very different, I think, later. Those hydrogen atoms will probably combine to make something that's a little less anxious.
Yeah, maybe.
And a little less self-aware. It'll be both better and worse.
Mm-hmm.
Is there a chance that some of the hydrogen atoms inside of me, and this may not be an astrophysicist question, but is there a chance that some of the hydrogen atoms inside of me will later be inside of another living thing?
Oh, yeah. Yeah, almost certainly. I mean, I don't know what your plans are in the long term, but at some point something will probably eat part of you.
Yeah, Crown Hill Cemetery, right here in Indianapolis. Home to more dead American vice presidents than any other location on Earth.
Oh, great. Yeah. Well, good company.
People say Indianapolis isn't a cool town, but, we got some stuff going for us.
There you go. I mean, you're also your atoms are kind of cycling around quite a bit anyway, right? You're losing skin particles, and things are eating those dust mites and so on, and so it's kind of a constant process.
Yeah.
Yeah.
This is a reminder for me that the main character on Earth is not any individual or even our species, but sort of the overall utter strangeness of life, that, we're part of a much larger Earth web that's part of a much larger universe web.
Yeah. Yeah. What's amazing to me is that we have so much of this story, that we can tell so much of the story, that we can look into the sky and see the time when the universe was just beginning. I mean, I guess we'll talk about the cosmomicrowave background more. But when we look at that background light, like, what we see is just a universe that's glowing because it's hot. Like, we see that the properties of that light just show us that this is thermal radiation. This is just the glow that happens when things are hot. And we can see that the early universe was just this hot place. And we can look at it. Like, we can directly look at it. There's no sense in which it's not just directly looking at it when we pick up that radiation. So we're just looking at the beginning of the universe.
Right. And is there a sense in which everything, like, I don't want to make it too much of a sphere, but is there a sense in which everything that we see and observe and are part of is kind of inside of that cosmic microwave background radiation?
Yeah. Yeah.
Like, can I think of it as a sort of a second extremely large Earth?
Yeah, I mean, it's a sphere. It's a shell. It's a bright shell of radiation that we are encased in, right?
And not just that we're encased in, but like everything that we can see in the universe is encased in.
It's the backlight for everything we see in the universe. Yeah.
That, again, makes me very happy. I like that. I feel its warmth.
Okay, good. Yeah.
Thanks for listening to this first episode of The Universe. Listen, even though I'm not a scientist and Dr. Mack kicked us off by saying that astrophysics can't answer questions of meaning, there is this huge sense to me that unpacking the wild strangeness of life and the universe in which life happens is a profound way to make meaning. Like, the more I understand myself as part of the Big Bang, the more both anxious and relieved I become about everything else in human experience. I don't know, I just can't really get enough of this stuff, and I hope you'll join me through this season as we stare into the void, which it turns out is not a void, because for some reason we can't explain there's more matter than antimatter. And my goodness, that is meaningful, even if I'm the one making the meaning. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, and mixed by Joseph Tuna-Medish. Our editorial directors are Dr. Darcy Shapiro and Megan Modaferri, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.